In this lesson, we will look at fuel distribution systems. The aircraft fuel system is designed to store and deliver fuel to the engine fuel system. It must be capable of delivering more fuel than the engine can possibly use in its most critical phase of flight, so that the engine is never starved of fuel. Big jets, such as the Boeing 747, can burn as much as 10,000 kilograms per engine per hour during the takeoff phase. Here is a diagram of a simple, single-engined light aircraft fuel system. The fuel tanks are rigid tanks fitted in the wings. They are filled by an open-line refueling pipe through a filler cap on top of the wing. The fuel is drawn from the tanks by a mechanical or electrical fuel pump. Through a hand-operated tank selector, which allows the pilot to use the fuel from either the right or left tank, or turn off the supply completely. The fuel then passes through a strainer, which filters out any foreign objects and debris before being delivered to the engine carburetor. Piston engines often need to be primed with fuel prior to engine start. This is achieved by use of a hand-operated priming pump, which takes fuel from the filter housing and delivers it to the engine inlet manifold. The fuel system is monitored for contents using simple float-operated level sensors, and fuel pump operation is monitored by a fuel pressure gauge. Drain valves allow any water in the fuel to be removed before flight. Multi-engined gas turbine aircraft have more complex fuel systems. To cope with the extra problems brought about by high-altitude operations, the use of multiple fuel tanks, and the need to feed the fuel to more than one engine. The fuel tanks are usually integral tanks in the wings. Many modern aircraft may also have a center tank, a tank in the center section torsion box between the wings. Some aircraft types also have fuel tanks in the fin or stabilizer, as well as being used to increase the fuel capacity. This fuel may also be used to change the position of the aircraft's center of gravity. There are a number of components and subsystems common to all multi-engined aircraft fuel systems. We will now look at these in some detail. The fuel tanks are fitted with a vent system. The purpose of the vent system is to allow the air pressure above the fuel in the tank to equalize with the ambient pressure. The areas above the fuel in each tank are connected together by a vent pipe. The ends of the vent pipe terminate in small vent surge tanks located at each wingtip. The vent surge tanks are vented to the atmosphere. The vent surge tanks are there to collect any liquid fuel which might get into the vent system during unusual maneuvering or because of overfilling of the fuel tanks. Any fuel caught in the vent surge tanks is returned to the main tanks either by gravity or by the operation of a pump. Some systems have float-operated vent valves fitted, which close to prevent liquid fuel entering the vent system. The EASA regulations require that when a fuel tank is full, a minimum of 2% by volume of the tank capacity is free of fuel to allow the vent system to operate correctly. If during refueling the fuel reaches this level, then the high-level float switch or volumetric top-off unit will close the refueling valve. As the aircraft climbs, the air pressure reduces. This in turn reduces the temperature at which the fuel boils, leading to excessive vaporization of the fuel. To help prevent this excessive vaporization at altitude, and to give a positive pressure of fuel to the pumps, ram air may be introduced into the vent system to partially pressurize the tanks in flight. This is normally done through ducts on the underside of the wings. Fuel booster pumps are normally fitted in pairs in each tank to pump fuel from the tank to the engine. They are a necessity in high-altitude aircraft to prevent bubbles forming due to cavitation or low-pressure boiling at the inlet of the engine-driven fuel pump. Each pump has a non-return valve associated with it to prevent fluid flowing back through the pump to the tank when the pump is switched off or has failed. Booster pumps are typically centrifugal pumps driven by 115-volt AC motors, providing a low pressure of between 20 and 50 psi with a high flow rate. There may also be a suction feed pipe to allow the engine-driven fuel pump to draw fuel from the tank in the event of a double booster pump failure. In the event of a double booster pump failure in one main tank, the Aircraft Emergency and Abnormal Procedure Checklist will invariably limit the aircraft to a maximum operating altitude to prevent fuel starvation due to cavitation or low-pressure boiling, causing vapor locks at the inlet of the engine-driven fuel pump. Filters or screens are used to prevent any debris in the tank being drawn into the fuel booster pumps. The booster pumps are fitted in a feeder box in the bottom of the fuel tank. This box is sometimes referred to as a collector tank or surge box. The feeder box should remain full of fuel at all fuel levels and aircraft altitudes. This allows the booster pump to be continually submerged in fuel, thereby preventing them from being starved of fuel and keeping them cool. Electrically operated engine fuel shutoff valves, or low-pressure cocks, are fitted to allow the engine to be isolated from the fuel supply. Cross-feed valves and pipes form a cross-feed manifold, which enables fuel to be fed from any tank to any engine. In this example, there are only 2 fuel tanks, so only one cross-feed valve is required. As we have already said, many aircraft have a center fuel tank. In this example, the fuel from the center tank is pumped into the cross-feed manifold on both sides of the cross-feed valve. The aircraft may also have a fuel tank located in the fin or stabilizer. In our typical system shown here, the fuel from this tank is pumped into the center tank for distribution to the engines. High-level float switches are used to automatically close the refuel valve when the tank is full during refueling, while low-level float switches are used to maintain a required minimum amount of fuel in the tanks during fuel jettison or dumping. Each fuel tank will have a fuel drain at the lowest point in the tank to allow water to be drained from it. In the event of the fuel tank being overpressurized due to a malfunction, a relief valve may be incorporated to prevent structural damage to the tank. The system is completed with the addition of a refuel manifold, which allows all the tanks to be pressure refueled from a single point. Shown here is the fuel tank layout on a typical 2-engined aircraft. The only difference to what we have seen so far is that the wing tanks are split into outer and inner sections. The fuel pumps are in the inner section. The outer section remains full until the inner has reached a predetermined level, at which point the outer section fuel is transferred by gravity to the inner. Keeping fuel outboard in this manner helps to reduce wing bending stress. On the screen now is the pilot's fuel control panel and a schematic fuel system diagram from a typical twin-engine passenger jet. The control panel shows selector switches for each main tank booster pump, accompanied by associated low-pressure warning lights which illuminate if the pump should fail or be switched off. The center tank pumps also have switches and warning lights associated with them. Suction valves in the main tanks allow the engine to be fed by gravity or suction by the engine-driven pump in the event of both booster pumps failing in one tank. There is a control switch and indicator light for the crossfeed valve. The light is illuminated when the crossfeed valve is open. There is a temperature sensor in the number 1 tank, which will transmit the fuel tank temperature to an indicator on the control panel. The engine fuel shuttle valve is closed by the operation of a fire handle for that particular engine. In some aircraft, it is also opened and closed by the selection of the fuel switch during the normal engine start or shutdown procedure. The fuel valve closed lights illuminate when the associated fuel valve is closed. The auxiliary power unit, or APU, takes its fuel from the number 1 tank via a suction bypass valve if there are no booster pumps operating, but it can be fed from any tank if a booster pump in that tank is selected on. The APU shutoff valve is typically operated by the APU automatic start or stop sequence. There are indicators which illuminate when their associated low-pressure fuel filter bypass valve opens due to a filter blockage. This filter is downstream of the fuel heater. Fuel from a pressure refueling system is fed in at the refueling station and dispensed to the fuel tanks as required. Defueling is achieved by opening the manual defueling valve. The booster pumps can then be used to pump fuel into a tanker. The normal sequence of fuel usage after takeoff would be to use the center fuel tank first, followed by the wing tank fuel. This sequence again helps to relieve the wing bending stress. The operation is achieved semi-automatically by switching on all tank booster pumps. Since the center tank pumps operate at a higher pressure than the main tank pumps, fuel is used from the center tank first. When its booster pumps can no longer pump fuel from the center tank, any remaining fuel can be moved to the number 1 tank by operation of the center tank scavenged jet pump. The main tanks will now feed their respective engines. The crossfeed valve allows both engines to be fed from one wing fuel tank, or one engine to be fed from both wing tanks. Fuel imbalance in flight between the number 1 and number 2 tank can be corrected by opening the cross-feed valve and then switching off the pumps in the tank with less fuel until the correct balance is achieved by supplying both engines from the tank with more fuel. It is important that this sequence is followed exactly, as there is a danger of starving an engine of fuel if the fuel pumps are switched off before the crossfeed valve is opened. When the correct balance is achieved, the previously switched off booster pumps are switched on again first, and then the crossfeed valve is closed. Again, it is important that this sequence is followed. This will restore what is known as tank-to-engine configuration. That is, number 1 tank feeding number 1 engine, and number 2 tank feeding number 2 engine. This diagram shows the fuel system from a modern, extended range, twin operational performance standards, or ETOPS, aircraft. It is very similar to our previous system, apart from a few additions to improve its reliability. The center tank is split into 2 parts, but it operates at all times as a single tank. The cross-feed valve is duplicated to provide redundancy. Normally, both valves move together as one. There are 2 shut-off valves in the fuel line to the engine. The spar valve shuts off the fuel as it leaves the tank system, and the engine fuel shut-off valve shuts off the fuel at the engine firewall. The APU has a DC electric fuel pump, which will switch on automatically if the APU is operated with no booster pumps operating. This pump will also automatically start, and the APU isolation valve will open to allow the DC pump to supply fuel to the left engine for rapid restarting in the event of a double engine failure. Some aircraft types have a fuel dump or jettison system fitted. This system is required if the maximum landing mass of the aircraft is significantly less than the maximum takeoff mass, and landing at the higher mass would compromise the structural integrity of the aircraft, or if the aircraft cannot satisfy the discontinued approach climb gradient required by the EASA regulations at its maximum takeoff mass. In an emergency, fuel can be dumped to reduce the mass of the aeroplane to its required landing mass. The fuel dump system consists of fuel dump pumps in each of the tanks from which the fuel is to be dumped, connected by pipes to fuel dump master valves and dump outlets. Typically, there will be a dump master valve on each wing at the outboard trailing edge to enable the fuel to be dumped safely with no danger of it entering the aircraft or any of its systems. On older aircraft, fuel dumping is controlled from the pilot or flight engineer's fuel control panel. On modern aircraft, the pilot has a selector knob which allows him to select the amount of fuel to be dumped or the amount of fuel to remain. The fuel dumping process will be automatically stopped when this level has been reached. If operation of the flaps or slats will cause the fuel being dumped to impinge on the airframe, a placard must be displayed warning the pilot not to operate the flaps or slats during fuel dumping operations. It would be clearly undesirable to dump all of the fuel in the aircraft, and safeguards must be in place to allow a minimum amount of fuel to remain. EASA regulations stipulate that the minimum amount of fuel remaining after dumping must be sufficient to enable the aircraft to climb to 10,000 feet and thereafter allow 45 minutes cruise at a speed for maximum range. This minimum fuel quantity is calculated at the design stage and the low-level float switches in the main tanks are calibrated to stop the fuel dump if this level is reached. That is the end of the lesson. Here are the main points you should remember. The fuel vent system uses ram air to pressurize the fuel tanks to help prevent vaporization of the fuel. The fuel booster pumps are 115-volt AC motor-driven centrifugal pumps, and they operate at pressures of between 20 and 50 psi. Their purpose is to supply a head of pressure to the engine-driven fuel pumps in order to prevent cavitation or low-pressure boiling causing a vapor lock at the inlet to the engine-driven fuel pump. The booster pumps are fitted in a collector tank or feeder box or surge box in the bottom of the fuel tank. This allows the booster pumps to be continually submerged in fuel, thereby preventing them from being starved of fuel and keeping them cool. The cross-feed valve or valves allow the fuel to be fed from any tank to any engine. Remember that when commencing cross-feeding, the cross-feed valve is opened before the booster pumps in the low tank are turned off. And when cross-feeding is complete, the pumps are turned back on before the cross-feed valve is closed. The purpose of the high-level float valve is to shut off fuel to the tank during refueling when the tank is full. Fuel dump or jettison systems are required on aircraft types where the maximum takeoff weight is significantly higher than the maximum landing weight. The fuel dump system must automatically stop dumping fuel when a defined reserve quantity of fuel is reached.